Well, we've just taken a look at the Rice expression applied in the simplest way possible. We basically started with the answer. We started with the equilibrium values at the bottom, something you never have to start, and we took those numbers out, we stuck them into the equilibrium equation, bang, got an equilibrium constant. There's your result. Well, that's a nice piece of fiction. It shows you a bit about how it is the Rice expression is put together, but not all that useful. The next example we're going to look at isn't any more real than this, but despite being a piece of fiction, it's a nice way for us to learn how to navigate our way around the Rice expression. Notice that in this particular problem, there's a bizarre collection of different kinds of information provided to you. I've given you the equilibrium constant, 3.8. I've told you a couple, not all, but a couple of the equilibrium concentrations, and just for good measure, I've thrown in a starting amount of something. So let's go ahead and write these all down, see everything they've told me. I've found out that this is 3.8 is equal to the ammonia squared over the hydrogen cubed times the nitrogen, so I know that that's true. I also know that as I write down this equilibrium expression here, that they've given me three numbers for some reason. They've given me, let's see, this number here is 0.2. This number here is 0.3, and I'm not sure why, but they decided to tell me that that's 0.4. So there you go. That's the information they provided, and they want to know the other 6 boxes. They want to know this box, this box, this one, this one, this one, and this one. So what is the first thing that we can learn looking at this? This is like one of those puzzles you did when you were a kid where they give you some of the boxes, and then you have to step your way through to find all of the others. It's pretty clear that the easiest and obvious box to solve for is this one down here in the lower right-hand corner. Why? Because this one here is actually the result of this equation that we see right up here in front of us. If I stick in my values for hydrogen as being 0.2, and nitrogen as being 0.3, and K is 3.8, I can solve for ammonia. And I do that. And you know what answer I get out? The answer I get out is about 0.1. It's not exactly, but it's close enough. Makes it for easier math later. So it's about 0.1 molar for my answer. In other words, 0.1 squared divided by 0.3 times 0.2 cubed is about 3.8. This is basically that practice problem that we looked at, that first example. Now that I have this, I want to take this to another step. And my next step is to figure out the next box that's possible. When I take a look here and I ask what the next box is, it's kind of like tic-tac-toe almost, between these two boxes right here is this one here. Can I, in fact, know what the change is that's occurring for my ammonia? It started at 0.04. It ended at about 0.1. So what is this value here? The answer is, of course, that it's an increase of about 0.06. It's an increase of about 0.06. Well, now that I know that stoichiometrically, guess what? Because everything must change in a 3 to 1 to 2 ratio, if that's 0.06, then this must be a change of 0.03 because it's half as much, and this must be a change that's 3 times this amount, or 0.09. And I know something about the signs, because if I'm making this, then these must be going away. Evidently, this is a reaction in which Q was less than K to start, and so the reaction is shifting to the right, which means these amounts of material are getting smaller, and this amount of material is getting larger. And of course, then I have my final result, which is to figure out these values that are up here to start. What number minus 0.03 is equal to 0.3? And the answer is that this would be 0.33. So 0.33 minus 0.03 is equal to 0.3. What would this answer be right here? This would be an amount equal to about 0.29. 0.29 minus 0.09 equals 0.2. I've now filled in this entire array. I started with a couple of ending concentrations at equilibrium, a starting non-equilibrium concentration, and 3.8. and then using a series of steps. This first step where I got my answer from K, the second step where I subtracted to find the change, this third step in which I figured out Q versus K to get the signs, and I used stoichiometry to get the 3:1:2 ratio, and then finally another couple of change calculations allows me to fill this in. Although we don't use this particular kind of calculation in real life, this is a really nice way for me to see how I can work my way around the Rice expression, gaining access to any particular cell that I want, depending upon the kinds of information that are made available to me.